So I went over, well, with a certain person, I went over Taylor polynomials. Are you interested in Taylor polynomials, or are you more interested in using second derivative test, positive definite matrices, negative definite matrices?
Yeah, I guess I'd be interested in a little bit of the Taylor polynomials, but more of the latter stuff that you mentioned.
Okay. Unfortunately, the sound system here is so terrible that I cannot hear you, believe it or not. I can, you're barely legible. And it's not the volume, we already tried. Actually try that. How about now?
Can you hear me now?
Yeah, not really.
Okay, I'll just type in the chat then.
Okay, thank you. Sure, how to actually ladder stuff. Okay. So let's come up with okay, so maybe we can try a function, and we kind of know with, how this function behaves. For example, we notice that this function has a minimum of 0 at the point 1, -1, 2. And if we multiply this out, I guess we can ask for the okay, if we represented the problem this way, I guess we could ask for the second order Taylor polynomial centered at some point. So for example, at the point 1, -1, 2. Okay, so we're going to find a second degree Taylor polynomial. Let's try, I'm going to try to check chat. Okay. If you have any specific questions, just to maybe trigger some something more relevant to you, like there's an exam review, I believe. There's the homework you turned in. we know that we're going to have the function at the center for the 0 order term. And then we'll have the derivative of the function this is going to be evaluated, and I should have said that at 1, -1, 2. And then we're going to have our second order term, and this is divided by 2 factorial. So then we're going to have 1 over 3 sorry, that's just 1 factorial. All right, so it's just a matter of computing derivatives. Avari, can you remind me in chat or tell me actually which section you're in?
I'm in McKeown section.
Okay. All right, so we're just going over some examples here of second order Taylor polynomial, and we're also going to use it to find critical points. Let me just lock the door real quick. All right, so now it's just a matter of evaluating a polynomial. I could have at least given it a +1 there. So that would be 1. And then we compute the derivative of f with respect to x. With respect to y. Easy. Okay. And we're going to evaluate it at the center of our expansion. And unsurprisingly, we get 0, 0, 0 by my choice. I chose the center to be a critical point, as it turns out, of a function. So the derivatives, or the first order derivative, will be 0. We also have to then compute the second order derivatives. Okay. So that will give us our Hessian matrix. Four, zero, zero. Well, that's an easy one. Okay. And that's just constants. It doesn't matter where you evaluate this Hessian. So we have that the second order Taylor polynomial turns out to be 1 plus, well, 0 because the derivative is 0. And over here we have okay. So just conceptually, are we going to have a local minimum or maximum at our critical point? So just to be clear, we know that 1, -1, 2 is a critical point of f because it made the first derivative equal to 0, or the gradient equal to 0, if you will. So do you know how to classify that critical point? I guess, do you want to talk about positive definite and negative definite matrices? I.e. the second, you want to use the second derivative test? Okay. All right, so now this, this matrix is going to be positive definite. So just to remind you of the second derivative test. If we know that the gradient at a certain point, let's call it A, is 0. So the first derivative is 0. And the matrix, the Hessian matrix at A, is positive definite. Then we know that f of A is a local minimum. And of course, if the gradient or the first derivative is 0, and the Hessian matrix evaluated at that critical point is negative definite, then f of A is a local max. Okay. So the question is, do we want to go over what a positive definite and negative definite matrix is? And if, one second.
Where is that?
We're going over positive definite and negative definite matrices. Okay. All right. So we have to figure out what does it mean for a matrix to be positive definite and negative definite. So here's some definitions and some equivalent conditions. So A is, first of all, supposed to be symmetric matrix. That is to say, A transpose is equal to A. And your Hessian matrix, as long as your mixed partials, if your function is smooth, your mixed partials are going to be equal. So if you look at the Hessian matrix that we wrote down over here formulaically, right, this is our Hessian. It'll be symmetric, right? This will be equal to that, and so on. And these are equal. It'll be a symmetric matrix. Okay, so what does it mean for a matrix to be positive, definite? Okay, well, it just means, just like if you had a regular function of just one variable, and you had a times x squared, right? We know that if a is positive, then we know that f of x is always going to be positive as long as x is not 0. So then, right, so if that's the case, or maybe you should start with that, if that's the case, you know a has to be positive. Okay. On the other hand, if f of x is always returns a negative number for any x not equal to 0, then obviously a has to be negative. That just makes sense, right? Because if the function is always negative and x squared is never negative, so a has to be negative. Well, the same definition kind of is used with matrix multiplication, except, well, matrix multiplication is in commutative, so instead of vector x squared, whatever that might mean, you have x transpose times a times x. So where we assume x is a column vector. So that's kind of going to look like what we wrote down here, right? Like x transpose, if you will, or h transpose times matrix times h. Right, so we say that if this always returns a number which is positive for any vector not equal to the 0 vector, then in some sense we say matrix A is positive, and we say it's positive definite. So this is what it means for A to be a positive definite matrix. Now, okay, so this is the definition, if you will, right? What are some equivalent conditions? What are some equivalent conditions for a matrix being positive definite?
Oh, my professor taught us 2 tests. One is the determinant. If all of the determinants is positive, it's going to be a positive. For all of the eigenvalues associated with that matrix is positive.
Yeah.
The matrix is positive.
So it's one good characterization. All eigenvalues. Now this is a real symmetric matrix, so all the eigenvalues are going to be real numbers. You're not going to get complex numbers where, like, saying that the eigenvalues are positive or negative make no sense. Okay. So all eigenvalues are positive is the same thing as saying the matrix is positive definite.
Oh, can I ask you a question?
Yeah.
So if it turns out that one eigenvalue is a complex number and the real number combined.
It won't happen for real symmetric matrices.
Oh, so all of symmetric matrices have
Real symmetric matrices. No complex entries, right? Yeah.
Oh, that will end with all real eigenvalues, real number eigenvalues.
Yeah.
Oh.
And now this proof will take you back to linear algebra. It's not a proof, I just want to connect. Oh, let me give you an example of why this, like 2, 3, 4, right? So this is a diagonal matrix. It's symmetric. What are the eigenvalues of this diagonal matrix?
2, 3, 4.
Yeah. This is a diagonal matrix, right? So the eigenvalues are just the diagonal entries. So this is a positive definite matrix. So it should make sense that if we take some position vector transpose times A, we should get something that's clearly always positive, right? As long as x, y, and z are not all simultaneously 0. So if you do this multiplication, you're going to get 2x squared plus 3y squared plus 4z squared, which clearly cannot be negative. In fact, it has to be greater than 0 as long as this position vector is not 0. Now, to kind of connect the definition above here, right, with this equivalent characterization of a positive definite matrix, you would have to go back to linear algebra and realize that since A is real and symmetric, it admits a orthogonal diagonalization. So we know that if you want to diagonalize a matrix, you're going to need some matrix P, then you have a diagonal matrix, then P inverse. Now the diagonal entries of this diagonal matrix are the eigenvalues. Okay, and in the case where A is symmetric and real, then we know that you can find an orthonormal parametrization, orthogonal parametrization where P inverse is just equal to P transpose. Okay. So then we have X transpose AX. We know that A can be factored. Okay. Which then you can think of P transpose X transposed diagonal P transpose X. Okay. And then we let P transpose X equals some vector Y. It's like a new coordinate system. Now, if X is 0, then Y has to be 0, right? And if Y is 0, X is 0. Why is that? Well, matrix P has to be invertible. It's, the transpose of P is the inverse of P. So we're going to get Y transpose, that diagonal matrix, and just for the, you get just the eigenvalues, the diagonal times Y. Where here we're thinking of Y as a vector with coordinates. So if you do this multiplication, you're just going to get lambda 1 times y1 squared, lambda 2 times y2 squared. And so obviously, if all the lambdas are positive, all the eigenvalues are positive, this has to be positive, right? Because you're squaring stuff and adding positive stuff. Okay. And the third test, or sorry, well, you have the definition and then equivalent characterization. So the third way to characterize positive definite matrix, or test for positive definite, let's see if I have some matrices, is to do the tests where you take the determinants of the principal minors. So you have the sequence of We'll do an example so it's clear. And if all these are positive, then you have a positive definite matrix. So let's see an example. Matrix A, a different matrix A than from above. So delta 1 is the, or D1 is the determinant of the upper left 1 by 1 matrix, right? So the determinant of 2 is just 2. Then you have the determinant of the 2 by 2 upper left matrix. So 6 minus 1 is positive, delta 3. It's just the determinant of the original matrix, so the 3 by 3. 4. It's 2. It's 2. It's 20. Minus 18, so 2. That's positive, right? So all these determinants are positive. And that's equivalent to the matrix being positive definite. So that's, and so I guess in principle, we could also find the eigenvalues of matrix A. And if they all turn out to be positive, which they should, right? Which they will, it's a positive definite matrix. Okay. So now what does it mean for a matrix to be negative definite? So I'm just going to write bigger, I think. So again, A is symmetric. And then we say that A is negative definite. DF for definite. Not good practice to use DF as an acronym. In calculus, so negative definite means what? X transpose AX is always going to return a negative number, as long as, of course, X is not 0. Okay. And in terms of eigenvalues, how do you characterize a negative definite matrix? A has all negative eigenvalues. Again, it's a real symmetric matrix, so the eigenvalues are real numbers, so it makes sense to call them negative or positive or neither, right? Or 0. Okay. And then the test, the determinant test, would be like so. You start that with a negative determinant, the upper 1 by 1. So let's keep it that. So here the 1 by 1 determinant is obviously negative. It's the determinant of negative 3. And that's not an absolute value. That's a determinant symbol there. So, okay. And then delta 2 should be positive. So this determinant of this 2 by 2 matrix should be positive. It's 12 minus 4, it's positive 8. And then the determinant of the whole matrix should be negative. So for a negative definite matrix, there's this alternating pattern of minus and plus. You start with a negative, right, with a negative determinant. So this entry has to be negative. And then you go positive and you alternate. So it's alternating negative, positive, but starting with a negative. This will keep going, right? Does this determinant equal?
Well, so I have a question.
Yeah.
What's independent? Definite?
Some indefinite?
Yes.
Sometimes positive, sometimes negative.
Is that sometimes positive, sometimes negative?
No, but we're talking about the matrix being indefinite. I'll show you an example, I guess. It's but we complete this determinant and we get negative 12, 0, 0, 0, negative 3, negative 4. Oh, I'll show you why this is. I'll show you a very obviously negative definite matrix and why this pattern of determinants has to. So that's negative, right? Yeah, negative 5, I guess. So yeah, this passes the test for a negative 3, positive 8, and negative 5. So that's A is negative definite. Passes the test. So here's, maybe this will so here's a matrix which is obviously negative definite. Right, if you write out the quadratic form associated to this matrix, it would be negative x squared minus 2y squared minus 3z squared. So I'm sorry, I'm using x as a position vector and then x as a coordinate, so I have to be careful. But that's clearly negative, right? For non-zero vectors. But do you see how the test for negative definite matrix, you get the determinant of the 1×1 matrix is negative 1. But then the determinant of the 2×2 matrix is 2 because you're multiplying two negative eigenvalues in the diagonal, if you will. And delta 3 would be negative 6. So it does alternate, starting with a negative. Does that make sense? Okay. Okay. Right. So now I'm gonna, does anybody have questions about anything particular? Because otherwise I have examples. So. Nope. Okay. And check chat. All right. So here's the function, and we're going to find all critical points, try to classify them. So you might want to try this on your own first. I'm talking about people who are watching the video or not actually at the review. So I'll just give you all the derivatives here. So does this function have any obvious minimums?
Oh, yes, it should have a minimum.
Where?
0, 0, 0, 0.
Well, so the minimum is 0, right? Anyway, but it happens along the whole plane, as long as x and z are equal. Okay. And so I computed some derivatives. And I apologize for the shorthand. I just don't want to write out x, a function of x, y, and z all the time.
You should also have settle.
Hmm?
You should also have settle. Settle.
You think so?
I am not sure actually.
Well, we'll see. I haven't really finished this. I just computed the derivative. So, you know, it's
Obviously there is no max.
that's not obvious to me at all, because what happens is we go off to infinity. Like if you're in space and you get arbitrarily far away, right? So think of this as, sure, x minus z squared, but you have e to the minus rho squared, where rho is the distance from the origin. So you have a polynomial and a exponential, which is decaying as you move away from the origin. In other words, well,
Actually, there is a max.
I think there will be. I think there has to be, because at infinity this goes to 0 at certain points. It's 0, so it has to be somewhere in between.
Yeah, because if you make the negative sign separate, so like you can write that e to the x squared plus y squared plus z squared to the negative 1. So which is going to be in the denominator? E is going to be in the denominator. And then x minus c squared is going to be the denominator. And then if you take Lobidro through infinity times, you will have e to the denominator left. Oh yeah, okay. I'm not sure if that makes sense, but
Well, to me, I just kind of think of it as it's 0 at some points, right? And then it's positive because it's a positive non-negative function. And then as we go away from the origin, this decaying exponential, you get like e to the negative infinity. So it's going to have to decrease. So at some point, it has a max.
Yes.
Okay. All right. Well, let me just write these down, and then we're going to find critical points. That would be fun. Good algebra. I'm not going to waste our time taking derivatives, though. Yeah. I'm sure you all know how to take partial derivatives. All right, so knowing the first derivatives, we can find critical points, right? So we set these equal to 0. All right, so we set those equal to 0. And the rest should be, well, let's see if that's easy or not. Well, obviously, the exponential function cannot be 0, right? So we can kind of cancel that out because that's always positive. So I guess looking at the first equation, if I label these equation 1, 2, 3, and 4, what are the cases that we get from the first equation?
X equal to 0, and then 1 minus x squared.
Well, hold on. X equals 0.
X equal to z.
Oh, gotcha. X equals z.
Z.
All right. My apologies. So, yeah, from equation 1, we have the case where x is either z or it's not. Okay. Now, if x is z, what about the second equation and the third equation? Well, you just get that 0 equals 0, right? So z has to be x. Y can be anything in this case. And then, okay. So we have an infinite many critical points, and they all take this form. Let's just say t's, y is anything, t. Or I can say x, y, x. anything of that form makes these derivatives simultaneously 0, as long as x is equal to z. Okay. All right, so I said we can ignore these because that's positive, so I'll just. So then if x is not equal to z, that's weird. Right, okay. Then what, from the first equation, what does have to equal to 0?
Let the right hand side of the x minus z to the right. That thing has to be 0.
This has to be 0, right?
Yeah.
Okay. Well, what does this tell you about the relationship between x and z?
We can solve this if you want to using the quadratic form, but it's like a bit too complicated. Like a b squared.
Yeah, we could do that. Not so. If I just write this as x squared minus, say, zx minus 1 is 0, right? I can quickly use the quadratic formula, sure. So x would be.
Oh, actually, is there less?
I would use
you
the
have to because
yeah.
you use the
Third equation.
Yeah.
So if we use the quadratic, we would get a relationship between x and z. Right? But that doesn't look very convenient. Like, I don't know. So what somebody's suggesting here is that we actually use equation 3 as well. Right? Because if we know that x is not z, then we know that this vector here is not 0. So the other factor has to be 0. So 1, let's write this as minus z squared plus xz 0. Okay. Now subtracting one equation from the other, what happens? So we decided against the quadratic. It times here, I see. Let's subtract one from the other. And we get that minus z squared minus x squared is 0. Okay, so x has to equal to z? Is that what we're saying?
Plus or minus z.
Ah, okay. So factoring this, we see that either z equals x, but we know that it's not the case because we're in the other case, right? So this is not possible for this case. Okay, I think that kind of resembles the word possible. Or this is 0, right? So x has to be the negative of z. Okay. Now, if we know that x is the negative of z, can we actually find what x and z might be? Well, sure. It's a system of, we're looking at this system of 2 equations, 2 unknowns. We've got a bit of, well, so we have that x equals negative z. Go back to any one of these. Say this, right? And we just replace z with negative x, I guess. So we have x times z becomes minus x squared. We started with this equation, and then we just said replace z with the negative of x. Right. So we get that x squared is a half, so x is plus or minus 1 over square root 2. And so what does y have to equal?
Y is 0.
Oh, well, what does z have to equal?
Plus or minus 1 over.
Yeah. It's just the negative of x, so I'll write that as minus plus, and hopefully we can remember that they're associated, those signs. Okay. So we have that, we found that x is plus or minus this, and z is just the negative of that. And correct, somebody pointed out that if you look at, we haven't looked at the second equation for the second case yet. X is not Z, so this is not 0. This is never 0. I should have erased that. So Y has to be 0 from the second equation. Okay, so Y equals. All right, so we have infinitely many critical points. Well, there's infinitely many of them that act the same way. So our critical points, X is anything, then you have Y is anything, and then Z has to be X. That's from this case. And then we have X is a plus or minus 1 over 2, Y is 0, and Z is just the negative of X. So that's 2 more critical points. So I better write that out because I don't want the ambiguity is that it's either one's plus or minus, so there's actually 4 of them. There's actually 2, just 2. This one and this one. So let's just erase that because people will get confused. So these are all the critical points. So we want to classify what happens at these critical points. So what do we need?
The second part of the test.
Yeah, we need the second derivative test. So
For the Hessian thing.
yeah. So I'm just gonna write out what the second order derivatives are real quick. How many do we actually need to figure out the whole 3 by 3 matrix? Just need 6 of them, right, because of the symmetry.
Yeah, we need the D1 square, D2 square, D3 square, D1 2, D1 3, D2 3. 6, yeah, 6.
I'm just gonna write out my results. Yeah, so doing these derivatives isn't too much fun, but it's not too difficult, so I guess you can think of it as relaxing. I don't know, I just didn't use brackets on the outside, parentheses on the inside. All right. Also, this went a lot quicker because I used shorthand like that. So when I did it. All right. And we need some of these are XY here. Probably edit this portion out of the video where I'm actually writing stuff down, so I apologize for you who are actually attending in person. And one more. I just didn't bother multiplying these out because nice things happen, right? When you plug in the critical points. All right, so first of all, what does the second derivative tell us at this type of critical point? The one that's like where x and z are equal and y could be anything. So so if we look at the Hessian, which I'm not going to write out, but we evaluated at, let me just to be clear, this is like x is a, y is b, and z has to be a, right? So we don't. Right, so let's see. Let's write down the expression for fxx here. Now evaluate fxx where x and z are equal. And what do we get? 2, 1 minus, well, times 1. The middle term would be 0. That's just 1. And then you have this not so cool.
So that's 2a squared.
Why do you say 2a squared?
Do you see like it's 1 minus x squared plus xc? So x equal to z. So x times x is x squared. Yeah. Am I correct?
It doesn't seem like it, right? If x and z are equal, this becomes 1, this becomes 0, and this becomes 1.
Oh, never mind. Oh, okay. You skip all of it. Okay. I was looking at the first time.
All right, so what about fxy?
0.
Why is it 0?
Fxy.
Yeah.
Oh, okay.
No, you're right, because x and z are equal.
0. Why is it 0?
And y is 0? Because y is 0, for example. What about fxz?
Negative.
The middle term is 0, the last term is 0.
Oh, so that's where did you put that? Do you see fxx? Where do you put the 2? It should be like 2 times 1 minus.
Oh. It's here. Is that good?
xz. 2 minus 1.
What's fyy? 0. At our critical point, of course. fzz is what is this? Mm-hmm.
That fxz, shouldn't that be 2 times negative 1 minus 2x?
Do you want to come up there and point to it?
Yeah. Do you see on here?
Yeah.
This is x. Where's x? Okay. On here.
Yeah.
We have. This is going to be 1.
Yeah.
1. This is a minus 2x.
Yeah.
This is a 0. Oh.
No,
never
yeah,
mind,
yeah,
never mind.
that's 0.
Never mind. Oh yeah. 0.
Okay. So I'm getting 2.
Oh, this is making my head like
Now,
this.
yeah, but there's a point that we shouldn't have done this, right? Why not? we're trying to classify what happens at the critical point A, B, A, where x and y are, or x and z are equal. So if you look at the original function, well, we already determined that has to be, the second derivative test would fail. If you look at this matrix, the determinant of it is 0, so the second derivative test fails.
Oh, yeah. Wait.
Oh, and I forgot, that's not a 0. Symmetric matrix. Okay.
Okay, the determinant equals to 0.
Yeah.
So the Hessian equals to 0. So the second derivative test fails.
But that's okay, because we already determined by, so we had to use something else, but we already determined that the function ABA is just equal to 0, and everywhere else it has to be positive, right? Or non-negative. Because of just the nature of the beast here. This was defined as x minus z squared, that's not negative, and an exponential is never negative. So when the second derivative test fails, you do something else, like think about it.
Does it only think about it? No other.
Maybe, I don't know. I'm just saying in this case it's sufficient just to consider the function. But okay, what about the more interesting points, right? So just copy that.
So are you saying that the second partial derivative test can fail, but the point can still be a critical point, like a local
Yeah.
minimum max?
Obviously, yeah. The second derivative test fails to tell you to help you classify what happens at your critical point. But it could still be something like min or max.
Where do you get the example from?
I just made it up before, like an hour before this. Okay. All right, but what about the other critical points? So the other critical point, remember, was, let's do the one that x is positive, say. Right, so this is a critical point. We want to classify what happens there. So we're going to create our Hessian at this point. All right. Let's see if we can do this without crying too much. fxx. Or maybe tell me which partial derivatives or the second order, which of these would be 0?
Everything containing y, fyz is going to be 0.
Yeah. Anything with a what? Well, hold on, I don't know.
Yes, only fyz.
Okay, let's check then. All right, because now x and z are not equal. In fact, they're negatives of one another. So. All right, so fxx at our critical point. That's 2. That's going to be,
That's a 0.
that's a 0, right? So I'll just write it out once for people. So 1 minus x squared plus x times y. Well, x and y are opposite in sign, so you get a negative 1/2. So indeed it's 0. So similarly, this will be 0 as well, right?
Yeah. The last one.
I'll write it out anyway. For this just this one time. All right, and then some business here. So and y is 0. We remember so there. Yeah. All right. So 0, 0. 2, square root of 2, -2, -4. Anybody else get this? Okay. FYY will be wait a minute. No, please it ain't so. It's on the FYY is 0.
It's not 0.
Why not?
X minus C is.
Oh, because y is 0. Okay, I was okay. Gotcha. So FYI, thank goodness, man. All right, so you get 2, then x minus z becomes 2 over square root of 2.
Square root of 2. Square root of 2. It's the 2.
Remember that z is the negative of 1 over square root of 2. Y is 0. Y is 0. Okay. Cool. So you get -4 times that exponential. Okay. That's easy. Zero. That would be 0. Okay. Let's just see what this is telling us. Oh, -6. -6 times e to the -1. All right. fxy at our critical points. Let's see. This will be 0, right? At our critical point. So just to write that. Multiplying these, you get 1 minus the half minus the half. I already seen that. So this would be 0 at our critical point. About fxz or yz, whatever, at our critical point would be 0, yeah? Because there's a factor of, unless I not correctly differentiate it, that's a y, and y is 0. That whole thing is 0. All right, what about fxz? So we get 2. The first term is going to be 0. There's the second term. And the third term is going to be 0 as well. Okay. Okay, so that's all right. So how do we want to deal with checking? How do we want to check where this is positive definite, negative definite, maybe neither? Which test do you want to use? Do you want to find eigenvalues or?
I have a question. So can we factor out
Yes.
the coefficient?
E to the negative 1?
No, like 2e to the negative 1. Can we factor out that?
Yeah. If you're just checking for positive or negative definite, sure. That's a positive number, right? So we're going to get negative 2, 1, negative 2.
Oh, actually, wouldn't that be 2 to the e to the negative 1 cubed because we're factoring out the 3 columns, 3 rows?
Oh, yeah, you're right, cubed. Good point. Jeez. Thanks.
Okay, this is much simpler.
Yeah.
I'm happy with this.
Okay. But, and we're, obviously, if this H is positive definite, right, then this has to be positive definite or negative definite because that's just a positive factor. So we just can check whether this matrix is negative or positive definite. I mean, we could do it with the exponentials as well, but you know.
The determinant is, the first determinant is negative. Determinant 1. Determinant 2 is positive.
The determinant 3, we can, so here's 2, here's 3, the original. I'll just use 4, 12.
Negative, yeah.
So that's negative 10. Anyway, it's negative. So what can we conclude about this matrix?
It's negative definite.
That's right.
So it's a local max.
Mm-hmm.
Oh boy.
Oh boy.
I hope it's not going to be on the exam. I really.
No, definitely. I would hope not. Unless it's take home, right? Therefore, we can conclude that F, that this is a local maximum. And if we cared what it is, we can actually stick it in. X minus z, rather, squared times that. There you go. That's the maximum. Do you think anything would change for our function if we tried the other critical point? Let's look
I'm
at
not
it.
sure actually. Actually, I'm not sure because there's.
I mean, it's going to have to be a local maximum, right?
Oh yes, because
there's
you
a
plug it back to
symmetry.
the original function. If you plug this back to the original, everything is squared, so that should still
Yeah,
be
x minus z or z minus x, so it's squared, it doesn't
squared.
matter.
Yeah.
Mm.
So that should still be a local max.
Yeah. So you also see that, and if we did this one further, this would be a local max as well. And then we found that at any point that looks like this, the function is 0, and that's in fact a global, but whatever. Just is amen. Well, that's a involved example, but at least has 3 variables in there. Did you look at the practice? So when is your first exam?
This Friday.
Did you already look at the practice?
Oh no, I haven't started the review yet.
All right. So there were some in there that were kind of like this. So,
Like, I have 2 exams this week, so.
Uh-oh. Yeah, we can take a look at it. But, I mean, we're going to have to leave in several minutes. I just wanted to see what you have. I noticed this morning in e-learning that it was there.
Oh, do we have the access? Oh, yeah. Oh, where did you get to that PLTL, like peer tutoring page? Like, what? Like, I don't have. I have the.
Yeah, you
online
wouldn't
and
have.
I have peer tutoring.
Yeah, you wouldn't have it. I don't
Like,
think.
I have peer tutoring. When I click on peer tutoring, it doesn't give me anywhere that would get to a link. Do you see it?
That's because you need because you're a student and you would need a link.
Yeah, like here, I don't
Yeah.
have a link.
But can you hit weekly reviews?
Yeah, weekly reviews, so it shows nothing, so there's no comment.
I guess we just send you the link. How do you? I don't know. Maybe Lee can tell me how the heck do you get into the review? I don't even know. Isn't there like a link on our website?
Oh, maybe, yeah. Like, I know the time, but I never checked for any of the thing. Like, I just come to your in-person section. That's where I can ask you questions directly.
Study material, right? So.
Oh, yeah, practice.
So chain rule, directional derivative,
Oh, I need to.
some basic limits. Right, you have a function of 3 variables, find and classify critical points. So that's what number 4 is kind of like what we did. Hopefully simpler because it's just a polynomial.
So like the way my professor does is let y equals to kx, and then see if it's going to give you converge to a constant. Like so okay.
Well, this is kind of out of context. I don't know what you're referring to.
Oh yes, because for example, if I do this one, limit x y equals to 0, 0. Where is the function?
Okay. 1 second, I'll get it back.
Oh yeah.
So maybe I should be showing Lee or whoever I'll be showing them that I'm sharing this.
Do you have any students?
Yeah, Lee could be there still. Probably.
Entire screen.
Sorry. Being really slow today.
Like the way my professor taught us is, so you let y equals to kx, and then you replace it with equals to.
Oh yeah, that works.
Like this.
But how do you know why? No, that's not a proof.
Plus k squared x squared equals to like a limit. There's limit, and then this is kx squared over.
Oh yeah. So this will be a function.
Plus x squared. Right, and then.
Well, no. It's the x squared you're factoring out, not the k squared.
Sorry.
But yeah, so that'll be a function of k. Therefore, it's the limit doesn't exist.
K squared. Okay, this goes to k over 1 plus k squared. So since this is not a constant, this is what I'm talking. Since this is a function of k, which is not a constant,
right?
Therefore, the limit doesn't exist.
Exactly.
And then he also taught us that if, for example, if this converts into a constant, that still cannot be certain this limit exists.
What do you mean it converges to?
So if for example in some
limit
cases,
as k goes to something, I don't get that.
Like if so, we see like over here we can factor out this, and then we cancel out x.
Yeah.
And then in some cases we can cancel out k. Like in some cases, in some scenarios where k is cancelled out, and we have that with a constant, maybe
really?
5, like something like that. If that happens, like so this is the exact word that McKeown said. So if a constant happens, you still cannot
because your function could be unbounded.
Yeah, so you still cannot be certain this will be a.
So this is the problem, right? Something like that. Well, it's not a constant though. Crap.
I remember very specifically my professor said, even if it converges to a constant, you still cannot be certain that this limit exists.
Oh, because you just check lines.
Check line. Yeah. Like I remember he draw a ball and then a line something like this.
Mm-hmm.
Like I can't remember exactly what happened.
Maybe I'll do this 40 perhaps.
Yeah.
But tell me why using polar coordinates fails. So this is a good thing, a tip for the exam. Okay. So does this limit exist or not? Now, and I want you to try using polar coordinates, right? It's a really simple example. If you use polar coordinates,
So that's r squared over r sine theta.
so you're using polar coordinates, you get r squared over r sine theta. So that's r over sine theta. Okay, so now we know that if we're going to the origin, r has to be going to 0, right? As our point, oops, as our arbitrary point here goes to the origin, its distance from the origin has to go to 0, right? So as r goes to 0. So can we conclude that if we take the limit, let's take the absolute value, I guess, so we don't have to worry. It's true that this, as r goes to 0, this goes to 0, right? So why is it, so does that prove that this limit is 0?
R goes to 0. This goes to 0. We don't know theta, but theta, like the sine theta, is obviously between -1 and 1.
Mm-hmm.
And then since it's convert, if sine theta is -1, so r over sine theta is converging to 0 from left, and then if sine theta is positive, r over sine theta is going to 0 from the right. So they all converge to 0. So that should be 0.
Okay, so now so if you use polar coordinates, you're going to get your function of x and y is going to equal to some function of theta, say.
R
So
theta.
this theta is theta and some function of r. Okay, so it's not sufficient for the limit to be, say, 0, right? So if h of r goes to 0, is that sufficient for this limit to go to 0, the function? It's not. You have to make sure that g of theta is bounded.
I have a question.
Right. So the example here that I'm using, I'm just going to quickly. Is that notice that 1 over sine theta is not bounded, right? As theta approaches 0, that thing goes to infinity, right? So if we just take the right approach where theta is approaching 0, like so, so let's look at the number line, sorry, the plane, and suppose that we go to the origin along the y-axis. Then here we can just do that directly. It's not squared. So I'm gonna take the limit as we go to the origin. And clearly you're just gonna take if x is 0, you're gonna get limit of y. So y goes to 0 is 0. But notice that this y in the denominator, right? So y equals 0 is not in the domain of the function even, right? So this is the x-axis is not in the domain of the function. But we can still, and that's where theta, when theta is 0 or 180 degrees, right, we're on the x-axis. So we can probably find an approach to the origin such that theta goes to 0, if that makes sense. So maybe,
Can we squeeze 0?
so suppose we go to the origin along the parabola y equals x squared. Right, because then I know that my tangent is horizontal and the theta would be approaching 0 at the limit. So let's try another limit where y is equal to x squared. So we have x squared and y squared becomes x squared. In the denominator we have x squared. So x to the 4th, sorry. Right, because y is equal to x squared. All right. And so this becomes 1 plus x squared divided by 1 after I divide by x squared itself. And what is this limit? Well, it's 1. Right? So the limit doesn't exist. We get two different numbers. Going to the origin along the y-axis gave us a limit of 0. But going to the origin along the parabola, y equals x squared, gave us a different limit. So the limit doesn't exist. Because not all approaches yield the same limit. And so that's what I just wanted to warn people about using trig, right? It's not sufficient that r goes to 0 for the limit to be 0. It also has to be true, or it would be sufficient to say that this function of theta has to be bounded.
Well, when you say bounded, what does it mean?
Doesn't go below 1 over sine theta can go to infinity, right? As theta goes to 0. So you essentially have something like something that might go to infinity times something that goes to 0. That's actually indeterminate.
Oh, okay.
So that's the problem, right? So it's safe. So this would be safe, for example, x squared, y squared, right? Something like that you saw in your homework. Here you could safely use polar coordinates. Now, why is that? Okay. Because you have r, and then you have a function of theta, but notice this function of theta is bounded, right? It's at most 1. It can't blow up. It'll never go to infinity. The theta is not in the denominator.
Oh, yeah, because according to squeeze theorem. So
Yeah. So this, right? This is bounded. Whatever.
1 and negative. Oh.
Right. So that's going to be at most a half, right? So that squared would be at most a quarter. Not that it matters. I could use 1, but whatever. Let's just use 1. But the idea is that this function of theta had to be bounded, right? Now you can say that your function is at most r, and as you go to the origin, r goes to 0, therefore the original function goes to 0. So, but you have to make sure that this function of theta is somehow bounded, so it doesn't blow up. You don't get an infinity or minus infinity. All right. Well, I'm going to go downstairs. Less.
Oh, okay. Yeah, I'm sorry if I pronounced your name.
That's fine.